So last class we learned about different types of motion. We had rectilinear, which is motion that's in a straight line, one-dimensional. Now we have curvilinear, which is motion that is not in a straight line. So this is two-dimensional or more. And this here, we had position being S, which is a scalar. Now here we'll have position R, which is a vector. A little arrow on top means it's a vector. So, kind of an example of what this might look like. So let's say there's a particle going on a curved path. So maybe it starts here, it ends here. So this is initial, this is final. Here's the center of the curve where the coordinate frame is. So if we say our coordinate frame is here, y, x, then our vector, so this is our initial, and then this vector is our final. The displacement here, that's delta r. So displacement is the distance the shortest possible distance between the start and the end. Now position. So this is the r vector, is location in space. Now displacement, change in r. So displacement equals r final minus r initial. Shortest distance between start and end. All right. So now that we have position, then we can get velocity. And we know that we have r for position. Then velocity is r dot. So this dot is a time derivative. Dot means ddt, so r dot means dr dt. Okay, so that's just shorthand notation. So velocity equals r dot equals v equals dr dt. So we remember this from last class, but we can also write it just with the little dot. And then acceleration r double dot, because it's the second time derivative. So that equals v dot equals a. So the double dot would be d squared r dt squared, and the single dot is dv dt. Okay, now these are instantaneous because since the r is the position vector to the location space where you actually are right now, then this velocity is the instantaneous velocity. So velocity at that instant. So you'll have a different velocity vector here than you will at here. And velocity is always tangent to the curve. It goes in the direction that you're going. So here, velocity will point that way. Here, velocity will point that way. So now average velocity is going to be the velocity average over that interval. That is velocity, and then it's got the bar over it. The bar means average. So that equals the displacement. So delta r over delta t. Now you can see this is a little bit different because you have the delta sign rather than the d. So this d is infinitesimally small. The delta is not infinitesimally small. It's like an actual measurable distance. So instantaneous, average. Similarly for acceleration, average acceleration equals delta v over delta t. So this, delta r over delta t, that's going to be r final minus r initial over t final minus t initial, which generally t initial is 0. So it's still a vector, but it's an average over a measurable distance in time. It's not infinitesimally small. So then A would have v final minus v initial over t final minus t initial. Again, it is a vector, but it is over a measurable distance.